Welcome to a video on the applications of the gradient. We first mentioned the gradient when discussing the directional derivative in the previous video. In this video, we'll take a look at specifically what the gradient tells us given a function in terms of two variables. Remember, the gradient of f is equal to the vector in which the x and y components are formed by the partial derivatives of f with respect to x, as we see here for the x component, and the partial with respect to y for the y component of the vector. We refer to this in many applications. We would like to know in what direction to move so that f of x, y increases or decreases the most. This direction is called the direction of steepest ascent or steepest descent. The gradient actually gives us this information. So here are some properties of the gradient. If the gradient of f of x, y is equal to the zero vector, then the directional derivative of f of x, y will also equal 0 for all unit vectors. For this video, we'll focus on the next two properties. The direction of maximum increase of f is given by the gradient of f of x, y. And the value of the directional derivative at x, y, or rate of increase, is given by the magnitude of the gradient of f of x, y. Connected to this, the direction of maximum decrease of f is given by the opposite of the gradient of f of x. And it also follows the maximum decrease of the directional derivative of f of x, y, or rate of decrease, is given by the opposite of the magnitude of the gradient of f of x, y. So what this means is, for a snowboarder, the opposite of the gradient of f of x, y would indicate the direction of steepest descent or steepest decline, and on a hot metal plate, the gradient of f of x, y gives us the direction of greatest temperature increase. We do need to be aware, though, that the gradient will change as soon as we move from a given point. Let's look at a couple problems. Here we want to determine the gradient of f of x, y, and then determine the direction of steepest ascent from the point 1, 1, 0, and then determine this rate of increase. So the direction of steepest ascent will come from the gradient of f evaluated at the point 1, 1. So let's go ahead and find the gradient of f of x, y. Remember, this implies that f of x, y is equal to natural log x, y squared. So the gradient will be equal to the vector where the x component is equal to the partial of f with respect to x. So we'll have 1 over xy squared times the derivative of xy squared with respect to x. That'll give us y squared. And the y component will be the partial derivative of f with respect to y. So we'll have 1 over xy squared times, and then u prime would be 2xy. Let's go ahead and simplify this. We'd have 1 over x for the x component, and this would be 2 over y for the y component. So to determine the gradient at the point 1, 1, 0, we need to evaluate this when x is 1 and y is 1. This will give us the direction of steepest ascent from the given point. So we'll have 1 over 1, that's 1, 2. So this tells us the direction of steepest ascent. And then the actual rate of increase is equal to the magnitude of the gradient at the point 1, 1. That's going to give us the square root of 1 squared, that's 1, plus 2 squared, that's 4, or the square root of 5, which is approximately 2.24. Before we take a look at this graphically, remember the opposite direction of this gradient would tell us the direction of steepest descent, and the opposite of this magnitude would tell us the rate of decrease as well. And we'll show both graphically. So what we're seeing here is the surface in gray, and the point 1, 1, 0 is this purple point, and I plotted the gradient as the red vector here. And again, remember, it's pointing in the direction of maximum ascent or largest increase. So from this point, if we move in this direction, this would be the direction of maximum ascent, and the slope of this line is equal to the magnitude of the gradient, which was the square root of 5. Now if we go in the opposite direction, I plotted the tangent line in blue to represent the direction of maximum descent. So moving in this direction, the slope would be negative square root 5. Let's take a look at another example. The temperature of a circular plate is given by this function. At the point 2,1, determine the direction of maximum temperature increase and the maximum temperature decrease. And then what is the rate of increase and decrease? Again, all this information can be determined by the gradient of T. So let's start by determining gradient T. So to determine the x component, we'll find the partial derivative of T with respect to x. I'm going to go ahead and apply the quotient rule. So we'll have our denominator squared. And our numerator is going to be the denominator times the derivative of the numerator, that's 0, minus the numerator, so negative 4, times the derivative of the denominator with respect to x, so that'll be 2x. And the y component will be the partial derivative with respect to y, so we'll have x squared plus y squared plus 1 squared, and then our denominator times the derivative of the numerator, which is 0, minus the numerator times the derivative of the denominator with respect to y, that'll be 2y. Now we'll go ahead and evaluate this at the point 2,1. So if x is 2, our numerator is going to be negative 16. The denominator is going to be 4 plus 1 plus 1, 6 squared, that'll be 36. And for the y component, we're going to have negative 4 times 2 times 1, so it'll be negative 8 over the same denominator. And these do simplify. Here we'd have negative 4/9, and here we'd have negative 2/9. So negative 4/9, negative 2/9 tells us the direction of maximum temperature increase, which means the opposite of this vector would give us the direction of maximum temperature decrease. So 4/9, 2/9 would be the direction of maximum temperature decrease. And now to determine the maximum rate of increase and decrease, we need to find the magnitude of the gradient vector at the point 2,1. Let's go ahead and do that on the next slide. So we have the square root of negative 4/9 squared, that'll be 16 over 81, plus negative 2/9 squared, that'll be 4 over 81. It's going to give us the square root of 20 over the square root of 81, which is going to be 2 square root of 5 all over 9. Let's go ahead and get a decimal approximation for that. It's approximately 0.497. So 0.497 maximum rate of temperature increase at the point 2,1. And that means that the opposite of this, or negative 0.497, is the maximum rate of temperature decrease at the point 2,1. Let's take a look at this graphically. In gray we see the surface, in purple we see the point 2,1. Here we see the gradient vector in red, again pointing in the direction of maximum increase or maximum ascent. So the slope of that red tangent line, as we see here, represents the maximum rate of increase, which was approximately 0.497. And then moving in the opposite direction, this would be the direction of maximum rate of decrease in temperature. I want to mention one more thing about the gradient. The gradient and level curves have a special relationship. So here's the same surface that we just saw, and here we see the graph of the level curves. The gradient of f of x will always be normal to the level curve. So for example, if we want to know the direction of maximum temperature increase or decrease from, let's say, this point here, the gradient will be normal to this level curve. So the direction of maximum increase would be in this direction, and the maximum rate of decrease would be in the opposite direction. That's going to have to do it for this video. I hope you found this helpful. Thank you for watching.